Welcome to qnawire.
In this problem, we're asked to draw two different chair conformations in trans-1,4-dimethyl cyclohexane, which I have a skeleton structure of here, and we're asked to label all positions as axial or equatorial. So in order to draw chair conformations, we're of course first going to draw two chairs. So 1 and 2. And so remember that in a trans molecule, one bond goes upwards and the other goes downwards. So we'll go ahead and draw the methyl bonds in red and then all the carbon-hydrogen bonds, in blue. So in the methyl situation, we might say that we might label this as 1 in both of these. So 1, 2, 3, etc. So the methyl group, we might say one of them will go up, and the other chair conformation, it will go down. The other methyl, because it is trans, has to go the opposite direction. So in this case, we have a methyl going up, so it has to go down. In this case, we have a methyl going down, so the other methyl has to go up, like so. And then we just fill in all of the other bonds as such. These are, of course, the important bonds, being the ones with the strange things. We would have, of course, the bonds on the corners of the chair, and we would have the bonds in the center of the chair. And so the axial bonds are all of the bonds that are perfectly vertical, and all of the bonds that are angled, that are horizontal, more or less, more kind of in the plane of the chair, if you will, are equatorial. So every one of these vertical bonds is axial. I've gone ahead and labeled the methyl groups there. And now we can even talk about, even though it's not in the question, which of these is more stable. So when we're looking for stability of cyclohexanes, what we're really looking for is that bulky groups, the bulkiest groups, are placed equatorially and are not adjacent ideally. So in this case, the more likely chair conformation is this one on the right, because it places both of the bulky groups, the methyl groups, as equatorial rather than as axial.